Hello, I'm going to be explaining the basics of what I'm doing right now. I'm currently doing the Taylor series, which I was learning about for a little bit, but now I'm learning more about the whole thing about it. Just not a little bit of it, but like explaining how to use it in everyday life and everyday equations. So, sorry, looks confusing. So, Taylor series. Polynomials have a lot of nice features that make them some of the best functions to work with in calculus. Ex, sin x, and cos x aren't polynomials, but they do equal infinite sums of power of x called Taylor series, which is the next best thing. What are Taylor series? We introduced Taylor series to solve certain differential equations. Let's refresh our memory of how this was done. So we did learn this, but it was just a little bit about the basics of it, not using it in every single equation. Starting with a quadratic improvement to the linear equation of f near x equals a. So, estimate right now, the function of x would equal fa plus f prime a times x minus a, and plus 1 over 2f prime a times x negative 2a to the second power. It kind of repeats like that as you go farther into the powers, but right now it's usually just important to find f prime, and f prime prime. Now, making this better by including a cubic term. So it makes it more equal, where it probably would result in a better answer and closer. We add f3 over 6 times x negative minus a to the third power. This, in turn, can be made even better by adding a quadratic term. So to make it even better, we add f4a over 24 x minus a to the fourth power. And so it just goes on forever, it's basically saying, which I guess is a little confusing, and no one would do that. The end results of these tweaks is an infinite sum called the Taylor series of f centered at a. Infinite n equals 0, and as you can see, the rest of the equation. Here, n factorial is defined by 0 equals 1, and if n is greater than 0, n equals nx, n negative 1 times n negative 2 times 2 times 1. I may be saying these wrong, but it's just when you get into advanced math, I don't know if you even want to say them anymore. So let's get some practice with this idea. What are the first two non-zero terms in the Taylor series of sin centered at a equals 0? So, here, give me a second. Let me see if I can solve this. I'll try to explain if I get it wrong or right. So, let me look at this again, see if I could get a hint or something. This is a little hard. What are the first two non-zero terms in the Taylor series? Sin x. I don't think it would be negative. That just doesn't seem to make any sense. So it probably would be A or D. Just have to find out what would be best. Okay. I don't know if it would be 1. Maybe it would, other than x. Unless we added. I'm gonna try A. Right. Here, let's get an exclamation to make it a little more simpler. So it explains, let's define the function of x equals sin x. That the first few derivative of f are f prime x equals cos, f prime x equals negative sin, and f to the third power x equals negative cos. Plugging the center 0 into the derivatives, we get f prime 0 equals cos 0 equals 1, f prime prime 0 equals negative sin 0 equals 0, and f3, or f prime 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 0 equals negative cos 0 equals negative 1. So it almost seems like it maybe if we got to, I'm not sure if this is right, but if we got to f prime 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 prime, or f4, we would get negative 2. Maybe it has a loop to do that with that. Or I may just be wrong, but it seems like it could make sense based on the other answer. So since f0 equals 0, the first few terms of sine Taylor series are 0 plus 1 over 1x, or 1 over 1 times parentheses x negative 0 to the first power plus 0, 2 times x negative 0 to the second power. And then the rest of the equation, which goes on pretty long. Okay. Oh, also, I know my math teacher may be watching this. If he is, can you maybe define what the exclamation point means in math? Because I know he'll be watching this. So, if I know you probably will know what the exclamation means. So if you do have a basic definition of it, that would be great. Okay, let's continue. Later in this lesson, we'll find the complete Taylor series for sine. In the meantime, check out this plot. It shows the results of including more and more terms in sine's Taylor series. So, this seems look at this, 3 and 7. They look pretty relative. Even 5 and 9 look pretty relative. They have the same, graph. So, degree 2n plus 1 is what it is. Yeah, it seems like they're almost related. Can you tell? 1, 5, and 9. They kind of have, the same middle chart. Right in the middle. And then 3 and 7 also have a relative graph. But they seem to have almost, a repeated thing. But in, a relative way. Not, completely repeated, but in a somewhat repeated way. Does it look like we can entirely capture the sine function with a few terms in the Taylor series, or do we need all the terms? It doesn't seem like we need all the terms. Exactly. We probably could simplify it. Of course. No, that's incorrect. If we truncate the infinite sum in the Taylor series, but keeping only a few terms, the result is polynomial. No polynomial is periodic, like sine, so we can never hope to capture all the sines up and downs with one. So it's probably best to have every single one, so you can get the good answer and the most obvious answer. But the most terms we include in the truncated sum, more wavy it gets, and the more it looks like sine's graph. So we should be able to perfectly reconstruct sine x only if we include every term in the Taylor series. Like if we look at sine, when you see it, it kind of looks relative, like it almost has like the same chart as like a sine would. Especially 9, you can see that it starts to almost move like it. It's like not super close, but it still looks like it. You could tell that you could definitely tell that you will look at it and you would be like, oh, that's a sine. Okay. More precisely, if we define fx equals sin x, then sin x equals infinite over n equals 0, fn, n 0, and x to the power n. Which means the infinite sum of the right converges to sin. We'll see this idea come up again and again when we find the Taylor series for some other important functions next with e to x. Okay. Also, my math teacher, if you're able to identify this equation, this one, infinite over n equals 0, and this symbol too, the exclamation and this symbol are the ones that I currently know, but I constantly forget. So if you have a good definition, I'll also be good. Thank you. Let's continue. The exponential function. We left one loose end when we proved Euler's formula. We said that. So I did that yesterday, but I didn't record, so I could probably make another video on it, but I don't know if everyone would want that or not. Okay, so we can see limit n is infinite, so limit is infinite. 1 plus x over n to n equals ex. This is just the basic description and receive e to the x. But we didn't actually show that it's true. The Taylor series for e to x lets us see why this holds. To keep things simple, let's assume x is real for now. What is the Taylor series of ex centered at 0? So, at 0, so the limit would be 0. Let me see. It may just be x to the n. No, it's not. It's this. Let me see. Why? Because the derivative of ex is e to the x, and the derivative of e to the x is e to the x. More precisely, if we define fx equals e to the x, then we have f to the n, x equals e to the x, for every n is greater or equal to 0. By the laws of exponents, e to the 0 equals 1, so fn 0 equals e0 equals 1. Plugging this into the Taylor series formula with centering a equals 0, we end up with the equation that we want to receive. If we simplify it down, that's what we would receive. Now if we truncate the Taylor series for e to the x down to the first n plus 1 terms, we get the polynomial 1 plus x to the second power over 2 plus xn over n. This plot shows a few of these approximations for e to the x. As we can see, it gets more and more accurate. The more. See, it's almost like f1x equals e to the x. Right now it's not, but when you get here, it looks almost exactly the same. Does increasing n make the approximation better or worse overall? I think it would make it better. Yeah, that's correct. We can tell by this. See, as we increase, it gets more and more close to the answer. I don't know if we would do that forever, if that would result in the answer. I don't think it would. It probably would result closest as possible to the answer. But as we go further, we can see it gets closer and closer. It's still off, you could tell, but it's really close. That's right. We can prove it here, but the approximations do get better and better as we make n larger and larger. So when we write e over x equals infinite and limit n is equals 0, xn over n, we mean that the infinite sum on the right converges to e over x for all real x. Keyword real. In fact, this infinite sum is very often used to define e over x, or e to the x power. Now let's use e to the x Taylor series to prove the limit. The limit of n is infinite, and 1 plus x over n to the n equals e to the x, left over from our lesson on Euler's formula, which, yeah, I did do, which I said earlier too. To get started, let's write out the first few terms of 1 plus x over n equals n. So we can approximate this giant equation, which I would like to read, but it is very long and I'm probably going to mess up a lot of words. So here's the equation. I'll move it slowly. If you want to pause the video and see it, just do it now. This is what it will look like. So basically 1 plus x over n to the n equals this giant equation, which is hard to do. Okay, what does the sum 1 plus n times this giant equation, you can see, looks like when we take n to infinity. So let's see what would be the best answer. What would be best? It looks like this would be best. It seems like, because we probably should be starting with x. Yeah, that's correct. We can prove this by seeing exclamation. The first term 1 doesn't depend on n, so nothing happens with it. In the second term, the n cancels, giving us n times x over n equals x. For the third term, we have to rearrange things to get n equals n negative 1 over 2. And we can see by the giant equation. It's not as big as the last one, but if you want to pause again, you can look at this. And if I'm ever doing or going too quickly, you could pause the video. So when n is able to go infinite, 1, negative 1 over n goes to 1, and the third term becomes x to the second power over 2. If we do the same kind of rearranging for the fourth term, we end up with n times n negative 1 times n negative 2 over 3 times x over n to the third power. And then we can also see we receive these other equations, which are relatively the same, but you can write them in different ways. So when we take n to the infinite, the fourth term boils down to x to the third x to the third over 3. Doing this for every power shows that 1 plus xn to the n equals 1 plus x plus x2 over 2 plus x3 over 3. So in the limit as n to infinite is 1 plus x over n to n approaches this, we can see like it repeats on. So, which we know is the same as ex in other words, limit n to infinite in this equation. So I'm gonna pause here for now, and I'm gonna add on a video. Hello. Let me just check if this is recording. Okay. I'm gonna be recording and finishing my Taylor series that I'm currently learning. Yeah. Well, the part 1, we finished off on this basic equation. And it basically says that now that we have the Taylor series for e to the x, let's return to the trig functions sin and cos. So we're gonna find trig functions for them, because that'll be really useful for more than just calculus. It's used commonly in calculus, but maybe used a lot more in sine and cosine. We found that the two non-zero terms of sine Taylor series are sin x equals x negative x to the third over 6 plus continuing. By finding sine's first three derivatives with the help of the identities, derivative over derivative of x, sin equals cos x, and derivative over derivative of x equals cos x equals negative si. The question is, what's the fourth derivative of sine? Based on this equation, let me look at what would be the fourth derivative. So it should go sine, cosine, negative. It may be negative cosine. No. Yeah, that's kind of a little obvious. You basically can use it for graphing, just like rotations. That's basically it. You just have to rotate it, and that kind of receives the same answer. It's different when you're doing 1 or 2 or 3, but it's basically like rotations, which you do learn in 7th or 8th grade. So if we take 4 derivatives of sine, we end up back where we started. Summarizing what we know so far, if the function of x equals sine x, then f0 to 0 equals sin 0 equals 0. So as you can see, as it grows or primes grow, it just seems to more like decrease, but like kind of decrease, but also as a mix. It seems to stay pretty low though. It goes from 0 to 1 to 0 to negative 1. And f prime x equals sin x. So this is just saying what they would equal. So basically f equals sin, f1 equals cos, f2 equals negative sin, and then repeating. Use all this to find fn 0 when n is even. So we know that fn 0 would just equal, if it was even, it would most likely be cos. Then or sin. So yeah, it probably would be negative 1. So 0 wouldn't make that much sense. I don't believe it would be 0. I'm gonna look at it for a second, see if I can examine it. So n would be even. So it most likely wouldn't be 0. Maybe this. Oh. It's 0. It was between 0 and negative 1 to the n. They just seem most likely. I thought it would be not 0 due to it being just the function, no primes or anything. But I guess that just results in it. Let me see how it works. So if we start with sine and begin cranking down through the derivatives, we end up back with sine after 4 derivatives. That means fn 0 repeats if we increase n by 4. Since f2, 0 and f4, 0 are both 0, f2 plus 4, 0 equals f6, 0 equals 0, and so on. So it's basically saying that all even equals 0, which may actually be useful. I don't know what odd will be. It seems like we may have a repeating process with 1 and -1, based on the cosine being either positive or negative. And then the sign doesn't seem to change that much, no matter if it's negative or positive. We just took a huge step towards finding the Taylor series of sine, and it's all thanks to the repeating patterns and sine's derivatives. More precisely, if we define fx equals sin x, then fn plus 4x equals fnx, so fn 0 equals 0 where n is even. But what if n is odd? So I believe it would be 1 or -1. We can see that here, but it seems like it's changing. So you see it goes from 1 to -1. So it has to be one of those. It may be C or D, because if we solve it, we may receive the same exact answer. So negative n plus 1. So I believe it would be 1, since it is when cosine is negative, the 1 is negative. Oh, I guess that makes sense. I was thinking if cosine was positive, it would be 1, the negative cosine would be -1, so it would just be considered 1. But it seems like if we solve it, you can pause for a second and see all of this info. I'm gonna read it for a second. So it was just basically saying that how we turn negative to positive based on a certain prime, in which that's kind of the easiest way to do it. It wouldn't just be 1, because you would have to have an equation that would equal -1, but also 1. Okay, it took a bit more effort than what we put in for e to the x, but we still managed to find all the derivatives we need for sine Taylor series. As we can see by this big equation, infinite over n equals 0, fn 0 over n, x to the n power equals infinite over n equals 0, just the odds, in parentheses -1, n minus 1 divided by 2 over n, and base the same. So it seems like odds are different equations than evens. They have relatively the same, but instead of keeping it normal, you basically just need to divide and based on the odd number, and it usually will receive 1 and -1. It's just changing based on what the sin, actually cosine is. Here fx equals sin x, at the center a is 0. We can make this expression cleaner by writing n equals 2j plus 1, where j is greater or equal to 0, is an integer. We can do this since we're only summing over the odds. So this would just be considered the odds to make it more simpler, but it seems like it's either 1 or -1. So we have an equation, and it just will receive 1 or -1. And that's the same for the other one, sine. but instead it stays 0. As we can see by this, it's not positive or negative because 0 can't really be positive or negative. Like the exponential signs Taylor series converges for all x to sin x. Now we could run through exactly the same set of calculations to find the Taylor series of cosine centered on 0, but let's take a shortcut. Use the facts that the derivative of sine is cosine and to find out the Taylor series of cosine centered at 0. So we're doing sine x equals the infinite n equals 0. So let me see if there's any hints. Here's a hint. If you want to pause it, try to do it yourself, you can too. For many functions, sine included, we have a sum rule for the derivative of the Taylor series. As we can see by this giant equation, derivative of x equals almost what we're currently seeing now, but this is more simplified. So it'd be centered at 0. Maybe it would be C, because it seems like all the other equations have adding on to them, while C seems to have basically the same but no adding or anything to it. As you can see, like the top ones are n plus 1 and 2n plus 1, and also the same for B. So let me look at this one. So it may be slightly related since sine equals x. You can see 2n plus 1, but we want to find it centered at 0. I don't know if that affects it or not. Let me look at this to see. So, I think it may be C. Well, yes, it is. It seemed like the most made sense if, like, we weren't adding on anything special. It would just be 0, as we can see by the basic equation. We can see here, earlier we learned that the derivatives of a sum is the sum of the derivatives. This applies to most of the Taylor series too, as we can see by this equation. In particular, if we take the derivative of sine's Taylor series, we get this also, which is different but somewhat related, by the power rule, which you can see. If this is too fast, you can pause it. And this is just quite a lot to read, and it would be very hard to read it all. I could read it, but here, I'll read the power rule at least. Derivative or a derivative of x to the times x 2n plus 1 equals 2n plus 1 x to 2n plus 1 minus 1 equals 2n plus 1 x to 2n. So the derivative of sine Taylor series is infinite over n equals 1 and negative 1n over 2n plus 1 and 2n plus 1 x to 2n. I may be saying these wrong, which I probably am, but I'm just trying to explain them in the way that I understand them. Now the fraction of a number is a product of all positive integers less than or equal to that number. So 2n plus 1 equals 2n plus 1 times 2n times 2n negative 1 times continuing equals 2n plus 1 times 2n. as we can see by this. So it seems just like it's repeating constantly, but it's always less than or equal to that number, which means 2n plus 1 over 2n plus 1 equals 1 over 2n, this, which basically kind of makes it simplified for more easier solving. Finally, sin equals its Taylor series. The derivative of sine is cosine. So cosine equals that, and that's how we find sine, as you can see by this. So the equations, as we can see, to solve each equation, e to the x, sin x, and cos x, or cosine, we can see they all have different equations, but they can be put back to each other. And we also saw that here, how they can relate to each other. All are valid for all x, which is important for the applications we look at towards the end of the lesson. But in the next section, we find out that this is the exception, not the rule. Some functions don't equal their Taylor series anywhere. The geometric sum. In an earlier lesson, we used cake to prove that infinite over n equals 0 Rn. A radius equals 1 over 1 minus radius. At least for 0 is less than r, and 1 is greater than r, which was the case for that really interested us. So this is the next about the geometric sum, which does still relate to the Taylor series. Looking at it differently, this tells us that the Taylor series for fx equals 1 over 1 minus x, which center at 0 and 0 is 0 is less than x, and 1 is greater than x, is given by infinite over n0 equals x to the n power, without us having to compute a single derivative. But does infinite n equals 0 x n convert to 1 over 1 minus x for every x? It's okay to guess if you're not sure. So I don't think it would, because x will be greater than 1 and will always not be like this. It won't always be greater than 0 unless than 1, so I would say no. And it says correct, right on the money. Something fishy happens with x is greater or equal to 1. On the one hand, if x is equal to 1, each term in the infinite sum, infinite over n equals 0, x to the n, becomes 1. Keyword becomes, which means we add up an infinite number of ones. On the other hand, 1 over 1 net minus x isn't divided at x. 1, since we can't divide by 0. And we can see this by this explanation. Sometimes people say that 0 divided into 1 equals infinite. If you think about it, that doesn't really make sense, because 0 times 1 over 0 equals 1 equals 0 times infinite equals 0. Since 0 times anything is 0, and 1 certainly isn't the same as 0, so let's just agree that 1 over 0 is unidentified. Or basically, like, not questionable, not be able to be answered. Can't really put in an equation. Also, if x is greater than 1, then 1 over 1 minus x is negative, even though each term in the infinite sum would be positive. So it basically messes it up. The basics. Because x will always probably be greater than 1, as will commonly. When you start Taylor series, it may not, but before that, it usually will be more than 1. So that's the main problem. So what's happening here? In short, we ask too much of the Taylor series when we plug in x equals 1 or any value greater than 1. It simply doesn't work for those values. So it kind of messes it up, but that's going to happen a lot in actual calculus, so we need a way of solving that. A more precise way of saying that is that x values greater than or equal to 1 outside the Taylor series interval of convergence. Roughly, the interval of convergence, written as a minus r, a plus r, surrounds the center A and contains all the x that makes the Taylor series converge. Here, r is called the radius of convergence. So, let's find the radius of convergence for the geometric sum. When we look at the geometric sum in the last chapter, we found a formula for the partial sums. n0 xn equals 1 minus x to the n plus 1 over 1 minus x. This holds as long as x is not equal to 0 and is not equal to 1. We already know that geometric sum diverges when x equals 1, but what happens to the partial sums when x equals negative 1? So, when they converge, or would they stay the same? I'm going to say converge, it probably would be the opposite. That's weird. Let me see why. The convergence or divergence of the partial sums all comes down to what becomes xn plus 1 when we plug in x equals negative 1. Now, negative 1n plus 1 bounces back and forth between two values as we increase n, negative 1 and 1. That means negative 1n plus 1 doesn't converge because it can't settle down on one single value. So the geometric sum diverges for x equals negative 1. So I guess it's just all constantly changing down. It can't settle down on a single value, no matter how much you repeat it. So it just would diverge. What is the radius of convergence for the geometric sum? So, I believe it was 0. I mean, not 0. 1. But that may be different for the geometric sum. Let me look at this. So, let me see. It would be negative 1, 0, 1, or 2. I don't know if it would be 1. Because it says it diverges into 1. So, converge. Would that be 2? That doesn't really make much sense. It would be 2. But that's probably my best guess. I'm just starting into this, so I'm going to say, yeah, it is 1. Let me see why. So, x equals n plus 1 goes to 0 as n goes to infinite whenever x is less than 1. When x is greater than 1, on the other hand, x to n plus 1 goes to infinite. That means the geometric sum converges for x is less than 1, but diverges for x is greater than 1. Okay, that makes sense. The set of all x with x is less than 1 is the same as the open interval negative 1, 1. By definition, the interval of convergence has the form a minus r, a plus r, where a is the center of radius of convergence. So if we do some basic addition, we can receive that same answer. We can see writing negative 1, 1 as negative 1 plus 0, 0 plus 1. Since 0 is the center, we see that the radius of convergence is r equals 1. So that would be the basic. That's a little confusing. Let me see why. So the Taylor series centered at 0 for a function of x equals 1 over 1 minus x has radius of convergence r equals 1. This is unlike Taylor series for sin, cos, and e to the x, which converges everywhere, so we have r equals infinite. There's much more we could say about the Taylor series in intervals of convergence, but all of it goes beyond what we do in this course. So let's end our lesson with a few more applications instead. So now we're going to end off with applications. We've seen quite a few physics applications in this course. So as exchange of pace, let's look at how Taylor series aid calculation in statics. Statisticians often look for trends in the outcomes of large numbers of chance events, like the roll of several dice thrown at the same time. It's impossible to know exactly how a given die will land, but the outcomes 1, 2, 3, 4, 5, and 6 all have an equal chance of being rolled. So for a single die, the probability distribution for the possible outcomes is flat. But when we increase the number of dice, the probability distribution for the total sum, the value the dice can land on, takes on a bell shape. We can see. Can you see a bell almost like shape? It goes from more like a graph to this. Okay, so next. The bell shape is captured by a Gaussian function, which comes from shifting and scaling the graph of function of x equals e negative x to the second power. It also shapes like a bell in this equation too. I wonder why. Let's see if they'll give a basic thing. Integrals of the bell curve like 1, 0, e, negative x2 derivative of x give statisticians probabilities for witnessing certain outcomes in experience involving chance events. E negative 2 to the second doesn't have an antiderivative we can easily find, but we can get a great estimate for the integral using Taylor series. Using the Taylor series for the exponential function, this ex equals infinite is n equals 0, xn over n. To find out the Taylor series of fx equals e negative 2 negative x to the second, centered on 0. So it would be centered on 0, which seems pretty relative. So this probably wouldn't make much sense. I don't think it would. It just doesn't seem right. Let's just go up. So the function of x would equal e negative x to the second. So it may involve some addition. Maybe it will involve plus 2n. Maybe that would affect it adding, or plus 1. Or, maybe that would generally affect it. Here, let me see. So it was negative 1 and x to the 2n. That makes relative more sense. As you can see, I don't know. Maybe x probably need a better placement. It was close, but not quite close enough where it would result in the same answer. We plug negative x to the second into the Taylor series for e to the x. We get e negative x to the second equals infinite, n equals 0, parentheses, negative x to the second n over n. Now we can simplify the part involving x like so. So we could simplify it to negative x2 over n, or these other ones. So the Taylor series for fx centered at 0 is given by this equation, which was the answer. You can see. So we basically just need to simplify it down, and we can receive the answer. So, yeah, we can see the third one. It would equal the same thing. Because the exponential functions equals its Taylor series everywhere, we see by this equation for all x2. So we can see this chart. If you want to pause it, you can look at it. Okay, let's continue. For the plot, it looks like just the first three terms, like this equation, or negative 1 to the 0, x to the 0 over 0 plus negative 1, x2 over 1 plus negative 2, x4 over 2. It almost seems like a pattern equals 1 negative x2 plus 1 over 2x to the 4th. We can see it's a pattern. It seems like the negative 1 power increases by 1 and the bottom number increases by 1, while x's power increases by 2. You can capture the function of the interval 0, 1 pretty well. If we approximate e negative x2 using its fourth order Taylor approximation, in this equation, 1 minus x to the second plus 1 over 2x to the 4th on the interval 0, 1, what do we get for the value of this? 1, 0, e negative x2, derivative of x. So this is an approximation. So I don't know if that would affect it. So that would equal 1 negative x2 plus 1, 2 to the 4th. So if we estimate that, what would that most likely equal? Let me see if there's any hints. No, there's not. So if we what would be a good estimate? It may be 30, or it may be 25. I don't know, this seems quite confusing. It seems like plus, I think it'd be 1 over 5. Of course, I was close though. Not really that close, but that's estimate. You can pause the video to see this equation. But if we use the fourth order Taylor approximation, we find this equation, which is a rough estimate. And we can simplify it to this, which you can pause the video to see. And then if we ignore constants of integration, then the power rule tells us as in this equation. So the fundamental theorem of calculus is this giant equation. In short, the fourth order Taylor approximation gives us an estimate equals 23 over 30. So it's an estimate, which I don't know if we will get the exact answer, but a rough estimate is best. The fourth order Taylor approximation tells us that 1 over 0 e negative x to the second derivative of x is estimated 23 over 30, or 0.7666 repeating. Very close matching the actual value of 0.746824. So this is an estimate, which is actually very close. It's off a little bit, but it is close. Approximating difficult integrals is just one of the many applications Taylor series finds in the real world. As our lesson comes to a close, we can't resist mentioning one other use for the Taylor series, proving Ehlers' formula. Because I is equal to the square root of -1, we also have I2 equals -1, I3 equals -9, I4 equals 1, and I5 equals I. So the powers of I repeat, and because of this we can show a basic equation, I0, not 0, but this equals infinite n0, I to the power n, 0 to the power n over n, or this giant equation, which you can pause to look at. But the first infinite sum is the Taylor series for cos 0 or cosine, and the infinite sum multiplying I is the Taylor series for sin 0, as we can see by this equation, which basically is just I to 0 equals infinite n0, I to the power n, 0 to the power n over n, which is basically the first. And those equations from the first will also equal cosine 0 plus I sine 0, which could be useful to simplify these giant equations then. So Taylor series opens up a new and quicker road to Ehlers' formula. So in conclusion, review and reflect. The Taylor series of a smooth function f centered on a is given by infinite over n equals 0, fn to the a, or f to the n a over n times x negative a to the power n. Because Taylor series have much in common with polynomials, they make many calculations in physics, engineering, and statistics practical. That's very useful. And then we can finish the lesson for today. And I will be doing another video on limits and concatenating. I started this a while ago and finished all of these, and I still only have 2 more. I started making videos on sine and cosine, so I thought it would be nice, and now I only have 2 more to go. And next is going to be calculus fundamentals, which is probably going to be much challenging, but I haven't really seen how it would be like. Calculus is huge, so it's going to be really long. This is more like the basics that you use in calculus, like everything, all the equations and everything. If I messed up or anything, this is more just for my learning experience. I don't really want this to be a tutorial for anyone to learn calculus, because I don't think it would be that great for them. This is just me learning calculus my own way. I just wanted to record it to see how I do it. I appreciate if you watch the end of the video and wanted to say thank you. Thanks for watching, and I really appreciate it.